guys, welcome to my channel, Math for Teens. In today's video, we're going to be doing a calculus optimization problem. So we're going to be looking at a cone that when it's full, it has a maximum capacity of 36 pi cubic centimeters of water, for example. And we want to know what is the minimum amount of materials that we can use to make it. So that's essentially asking, what is the minimal area? So how do we solve such a problem? Well, the first thing is to make a drawing. It's always a good step. And define your variables. So here, if you don't really know what variables would be involved in this, it's a good thing to just remind yourself of what are the equations for volume and area of a cone. And I honestly didn't remember that. I had to look at a sheet of paper for this. But I wrote it over here. So we have the area is equal to pi r times s, where s is just the hypotenuse of the triangle with r, h, and s. So it's r squared, the square root of r squared plus h squared. And so your area is pi r times s, and your volume is pi r squared times h divided by 3. So r is just the radius of your circular base, and h is just the height of the cone. Okay, so there we have our variables. The next thing is to clearly identify what am I minimizing. So we're minimizing our area. And yeah, the next, but of course, if I want to find the minimum of something, a minimum is a spot where the derivative is 0, right? Like on any function where the slope of the tangent line is 0, it's going to be an extremity, either a max, a min, or a saddle point. So I need to first check for all points where the derivative is equal to 0, and then after that, if I get more than one, I'll check, is this maximum, is this minimum? I'll use the second derivative test for that. But the first step is just let's find the points where the derivative is 0. So which x values allow that, or are, I guess, here. So that means I'm going to be differentiating a. But when you're doing a derivative, it's relative to a variable, right? Like if I make a small change in this variable, how much will my area change? It's not two variables, and you can see that our area is right now a function of r and s. But we know s is just r and h. So our area right now is a function of both r and of h. But I can't really have that because right now, I'm not differentiating with respect to both of them. But that's why it's really handy that they already gave us the volume. They already gave us something to link r and h. So I'll just do that so you guys can see. So I have 36 pi is equal to pi r squared times h on 3. And of course I can just divide both sides by pi, multiply this side by 3, which gives me 108. And I can, okay, at this point you have to choose which variable do you want to be working with for the rest of your problem. And remember, this is what we're going to be differentiating. And I can see that h only shows up once. So instinctively, I'm like, I kind of just want to isolate h, like express h as a result of r, in terms of r, instead of doing r in terms of h, because I'd have to do like 2 more substitutions. So that's what I'm going to do. We'll see where that takes us. So I have h is equal to 108 divided by r squared. Although, yeah, we'll do it. We'll see where it takes us. Okay, so this is our new perimeter, I guess. And now we can redefine our area. So my area is now pi times r times the square root of r squared plus h squared, which is just 108 divided by r squared squared. Okay. Yeah. So now this is what I'm going to be differentiating. And the only variable is of course r. So we'll do that. So I prime is when the derivative of a with respect to r is 0, it means that a is either max or minimum. We'll just say it's a minimum, and so we'll have found our r value that satisfies that condition. So yeah, I'm gonna erase some stuff because I anticipate this will take a bit of space. Okay, so this is my a. I'm gonna take out pi completely, and well, okay, let me be good with my communication. So a prime is equal to, we're gonna take out the coefficient pi, and it's just a product rule. So we'll have r prime times the square root of r squared plus 108 on r squared plus r times, and of course you can write a square root as something to the power of a half. So we r times r squared plus 108 on r squared to the 1 on 2 to the half. And of course, doing the derivative of this, so prime. Okay, and we'll set this to 0 at the end, but yeah. 0, setting it to 0 just means we're looking for any points, any r values where the derivative is 0. Okay, so a prime, or I'll just do my equals, so equals, so the derivative of r with respect to r is just 1, so it's 1 times the square root of r squared plus 108 on r squared plus r, and we're just going to use the chain rule, starting with the outside derivative, which would be my power rule. So the half drops down, and you get r squared plus 108 on r squared. And now raise to the minus 1 on 2. We subtracted 1 from our exponent. And then now we're going to multiply this by the inner derivative. So that's 2r, so the derivative of this term. And plus 2 times 108 on r squared. And I now have the inner derivative of this term. So this is just 108 times r to the minus 2. So if I want to differentiate that, it's going to be, so times this term times so we'll drop down our minus 2 times minus 216 r to the minus 3. Okay. Yeah, so we have pi times square root of r squared plus 108 on r squared, and then plus, and what do I have anything I can use here? I think I'm just going to be clean about it and not rush the steps. So we can have r on top of 2 times the square root of r squared plus 108 on r squared. So this minus 1 and 2 brought it down to a square root on the denominator because it's negative. And then r times 2r plus, so 216, maybe I'll write this next to it. So times 2r plus 216 on r squared times minus 216 on top of r cubed. Okay. And yeah. Okay. So this is equal to pi times the square root of r squared plus 108 on r squared plus r, okay, times, so I want to bring this all into just like one big term. So I have, when I multiply these two, I get r to the 5, so I'm going to multiply this by r to the 5 to have common denominator. So times 2r to the 6 minus 216 squared. So minus 46,656. Yep, and divided by r to the 5. So I have my 2r to the 5 square root of r squared plus 108 on r squared squared. And of course we're setting that equal to 0. Okay. I can maybe do one more line. Sorry. One more line. The first thing I'm going to do is just, if I'm setting this equal to 0, I can just divide both sides by pi. Get rid of this. So that's gone. I also want to bring this now to a common denominator because once I've done that, I can also multiply both sides by the denominator, and then I won't have to deal with the denominator. So I need to bring this to the same base. So it'll be, I'll have to multiply it by 2r5 and then also by this. But this square root is the same as that, so when I multiply them together, it'll just be squaring this term. And the square of the square root just undoes itself, and I'll just get 2r to the 5 times whatever's inside my square root. So that's r squared plus 108 squared on r to the 4. Okay, we are running out of space. Plus r times 2r to the 6 minus 46,656. And then it was on this entire denominator. I'm just gonna pretend like I multiply both sides by the denominator, so it's equal to 0. Okay, so now I don't really want to have to solve this though, if I'm being honest. It doesn't look at all easy, but okay. Maybe this was the wrong choice in isolating the variable, but yeah, let me erase some lines now. Okay. So what do I have at this point? I feel like this was from a different step. Okay, I think that's what I have. So I have 2r to the 5 times r squared plus 108 squared plus 11,664 on r to the 4 plus, so 2r to the 7 minus 46,656 r is equal to 0. So what do I want to do now? okay, maybe what I want to do is bring these two to I'm going to bring these two to a common base. So I have 2r to the 5 times r to the 6 plus 11,664 on r to the 4. So it's just going to cancel with this. Plus 2r to the 7 minus 46,656r equals 0. So these are pretty much basically canceled. I have 2r to the 7 plus this times 2, 23,328r plus 2r to the 7. That would be really nice if those just cancel, but no. Okay, no. That would not be good. Minus 46,656r equals 0. Okay, so now I have 4r to the 7. Now this minus that, minus 46,656. So minus 23,328r equals 0. So, okay, and now I'm going to say, let's see if this is, that is actually, you can divide that by 4. So you can take out 4r, so I have r to the 6 minus 5,832 is equal to 0. And, I forgot to tell you guys a step that's important to solve these types of problems. And it's that you need to determine the domain of your function. Like what values are allowed for r. Where was my area expression? Okay. So what is this? That's my derivative. My area expression itself was like this. Still a lot to undo. But there may be some r values that are disallowed. For example, I don't think r can be equal to 0. So I think we're gonna have to set this being equal to 0. So, well, of course, r can't be equal to 0. Because I don't think it would have a volume then. Pretty sure. Like, no, obviously it wouldn't have a volume. Okay, sorry. So, that means that this term has to be equal to 0. So I have the r is equal to, and of course r has to be positive. In real life, like, lengths are not negative. So r is the 6th root of 5,832. So times -1. And how do I even, okay, so your calculator probably doesn't have a 6th root button, but you can just raise it to the 1 on 6. So raise it to parentheses 1 divided by 6. Not really a clean number. But I do have, maybe I can simplify this. I don't really want to do that. But it's approximately, the radius is approximately equal to 4.24 centimeters, 1,000 centimeters. So cubic centimeters because it was volume. What did the question want us to find? It wanted us to find the dimensions that minimize the quantity of fabric or whatever that's used to make the cone. So the dimensions that we were considering was radius and of course h. So if that's r, well this is r, is it a maximum or a minimum? No, and then I'll check, well, given that this is the r that gives you the minimum area, I'll find h. So I need to do, there's two ways you could do this. You could do the second derivative test. So where was my first derivative? I think I erased so much of my derivative and it was so like a bit ugly to be honest, that I don't really feel like doing a second derivative. So, but I don't even have my first derivative at this point. So I'll get back to this later. I'll redo it. I'll do the second derivative test when I actually have my full derivative in front of me. Because you guys should do that. Because you should always check, is the value that I have a maximum or a minimum? And sometimes you'll get more than one value, and it will be super helpful there to choose between the different values that you get, which one will actually give me my minimum area. I'm just going to go with this for now. As you can see, a few things have been done wrong in this video. But assuming this is, well, I know it's an extremum, I'm just going to assume it's a minimum. What would H be? So I already have my relationship from the volume was that, what did I have? My volume was 36 pi. Sorry, this is really small as well. 36 pi is equal to pi r squared h on 3. So that means 108 on top of r squared equals h. Okay, so r squared, that means that it's now the third root of this. So does this have so 5832 raised to the 1 divided by 3. Oh, a third root, a clean third root does exist. And it is 18. So h is 108 on 18. Is that clean? And that's 6! Yay! And h equals 6. We have hope, guys. It's always nice to see full integers. Okay, so I'm gonna need to erase some more. Okay, so I'm just gonna write here. Dimensions. So h equals 6 centimeters and r equals, I don't know if you guys like going with exact or non-exact. So the 6th root of 5,832, which is approximately 4.24 centimeters. And put that in a phrase. And of course, the things I didn't do in this video that you should do. So use the second derivative test. If the second derivative is positive, that means that your concavity is like going up, which means that any extremum that you have is going to be a minimum. And so if the concavity at this extremum is upwards, it means that it's a minimum. You could also just use the first derivative and do the variation test. So find all values where the first derivative is equal to 0 or undefined, as well as where the function can be 0 or undefined. Put it into a table. I did this in a previous video, I think, in my analysis and learning to analyze like graphics, and just see over which intervals is my first derivative going up and is it going down, and then at your critical number where your first derivative is equal to 0, you can see if it was going up and then going down, it would be maximum, or if it was going down and then going up, it would be minimum. So that's a little bit more visual maybe. And then of course find the domain. Yeah. Okay, well, thanks for watching, guys. I hope this helped. Yeah, have a good day.